Right, we're in about as good a day as we could possibly have to have a look at a solar panel in bright sunlight. It's early June, it's nearly local midday, and the sun is about as high as it ever gets in northern Britain. We're at a latitude of 54 degrees, which means that if the Earth's axis was vertical, as it is in March and September, the sun will be 54 degrees from directly overhead. But the axis of the Earth is tilted towards the sun, and we subtract 23 degrees from the 54, we get 31 degrees, and that's where the sun is right now relative to the local zenith. That means that the layer of atmosphere that the sun has to come through is pretty thin. It's nearly as thin as it would be at the Earth's equator, and so we should get the full intensity of the sunlight at the surface here, and that is about 1,000 watts per square meter. Okay, solar panel now is going to convert that 1,000 watts per square meter into electricity. Let's in order to see that, we've connected the solar panel to a little watt meter, and I'm about to connect the watt meter to a load. But before we do that, the solar panel, without any connection to the load, is producing a voltage, and we can see here that it's producing about, at the moment, 21 volts. But there's no current being extracted from the panel, and therefore we're not transferring any power from the panel to the load. In order to do that, I need to connect a load, which I'm doing now, and make sure that the panel is pointing directly at the sun. I've got a little sundial here, and now we're drawing current from the panel. If you'd like to have a look at the meter, now we're just getting about 24.5 watts there from the meter at 17.4 volts. Just one of the first things I'd like to have a look at is the effect of tilting the panel away from the sun, and we can use this little sundial here. I've marked the number of degrees that we are away, so I can, at the moment we're 24 watts coming out of the panel, 10 degrees off maximum, still 24, 20 degrees away, it's dropped to 23.5 there, and now I'm nearly up to 30 degrees, we're down to 22.5. So even though the panel is 30 degrees away from the pointing directly at the sun, we're still generating within 10% of the maximum power of the panel. And that's very useful if you've got a solar array. You can fix the solar array, and the sun can move by plus or minus 30 degrees, 60 degrees in the sky, and you'll still get close to the maximum power from the panel. Now, one other thing I'd like to demonstrate here is the importance of matching the load to the panel. At the moment I've got 4 50 ohm resistors, and that's dissipating the power from the panel. The panel produces electricity, the resistors convert the electricity into heat. This has been chosen actually because that's transferring a maximum amount of power from the panel to the load. Now if I disconnect a couple of these resistors, so that one and that one, the 4 in parallel are now just 2 in parallel, so we've gone from 12.5 ohms up to 25 ohms, and the power has now dropped to 15 watts. Okay, and so you see it's really important that the load matches the impedance of the panel, and this is a fundamental law of power electronics. In order to maximize the transfer of power from a source to a load, the impedances have to match. With a good solar panel, the panel is producing DC electricity. An inverter is used to convert this into mains electricity, and a good inverter will follow the impedance of the panel as the sun intensity varies and changes its impedance. Okay, I think that'll do for now.